What's up, Algebros and Broettes? We're doing math on the internet, so don't adjust your TV set. Let's get linear! Today in linear algebra, we're going to be taking a look at systems and linear equations. So let's go ahead and jump into it. This is our introduction to the material. So this is going to be a great place to start. First, we have a linear equation in the variables x sub 1, x sub 2, so on and so forth to x sub n, is an equation that can be written in the following form. And here we have a sub 1 times x sub 1 plus a sub 2 times x sub 2 plus so on and so forth plus a sub n times x sub n equals b, where b and all of these a values, a sub 1, a sub 2, so on and so forth to a sub n, are numbers. Typically, these are going to be real numbers for us. They could be complex numbers. We would know that information in advance. And here, we'd say that the x values are going to be what we're solving for. Those are our variables in the linear equation. And n is sort of where we stop. So depending on what n is, that means how many of these pieces, terms to the linear equation we're going to have. And our subscript for n really could be any positive integer. For what we're going to be doing, it's somewhere probably between 2 and 5, right? But in real life scenarios, if you're applying this in the real world, out in the world of work, you could have values for n that are as large as in the thousands. So we could get some pretty big systems that we could be working with. We have some examples of some linear equations. So here we have a linear equation right here. We got 5 variables. We got our constant coefficients. We got a number on the other side. Here I have another example, right? And it looks like we're missing x sub 2 and x sub 4 in the equation, but it is still a linear equation. And here I have another example, and this one maybe looks kind of funny, but you could, these are all real number coefficients, and if you don't really like how it's been kind of factored, what you could do is you could actually distribute that in on that left-hand side and get something that looks really maybe a bit more like what we like. A system of linear equations, known as a linear system, is a collection of one or more linear equations involving the same variables. Now we're talking about a system, sort of a collection of these linear equations. And here I have a system, right? I have 3 equations, 3 unknowns. So you can take a look. My 3 unknowns are x1, x2, and x3. And I have 3 separate equations to work with. And the goal would be to solve that system. We'd say that a solution to the system is a list of numbers. There would be numerical values. We would solve for what those numbers are. Maybe the numbers are like 2 and then -8 and then 17, something like that. But we just say a list of numbers, s sub 1, s sub 2, so on and so forth to s sub n, where those are numbers that make each equation. So in this example, I have 3 equations, for example. It would have to make each equation a true statement when these values are substituted respectively for x sub 1 and x sub 2 and so on and so forth. So I'd want to find some numbers for x1, x2, and x3 that make all 3 of these equations into true statements. That would be my solution. We say the set of all possible solutions is known as the solution set of the linear system. And in some cases, we might only have one solution. In some cases, we may have many solutions. We may have no solution. We would say 2 linear systems are called equivalent if they have the same solution set. That is, each solution to the first system is also a solution to the second system, and vice versa. And there are 3 types of situations that we could sort of encounter when we're looking for solutions of these systems of equations. We could have one solution only, we could have no solution, or we could have infinitely many solutions. And let's see how that would look visually. So let me get sort of graphical representation. Let me draw my grid axes. Think of it sort of like the traditional sort of graphing. And let's get a different color here. So let's say I have, we're talking about linear equations, so let's use lines. These are my equations in this first example. We'd say, well, where is our solution? Well, our solution is where we're going to intersect. So right there. And so this would be one solution, or we call it a unique solution. So one solution. As opposed to, we could have a situation where we have, say, no solution. So that could be my first line, and then let's say we have something parallel with a different intercept, same slope though. We'd say in this case we have no solution. Or that third possibility is that we have many solutions. When we say that, we mean infinitely many. So let's say this is my first line. And then to have infinitely many solutions, well, I would need another equation that really isn't, it's the same one, right? It really is the same equation. So I'm just sort of tracing back over very carefully this line that I already drew. So if you speed through the video, you'll maybe miss what sort of happened there. But in this case, we actually have infinitely many solutions. Anything on that line would be a solution. But, for example, as they're there, all these solutions everywhere. Are there other ones? Of course. I'm not going to circle all day for you, but you know what I'm getting at. Say a system of linear equations is said to be consistent if it either has one solution or infinitely many solutions. So we want to know, is there a solution? If there is a solution, then we say it's consistent. A system is said to be inconsistent if it has no solutions. So here we'd say this is consistent. We have a solution. This is consistent. We have a solution. And then in this case, where we have no solution to the system, this is inconsistent. And that's what we're working with. Let's talk about matrix notation. How are we going to write for the rest of the semester working with these matrices? We can write all of the important information that we need for a linear system into a rectangular array known as a matrix. So for example, here I have a system of equations, two unknowns, 3x1 plus 6x2 equals -3, 5x1 plus 7x2 equals 10. And we can start by talking about what a coefficient matrix would look like. So in this case, for my coefficient matrix, I like to start with sort of my empty box. Coefficient matrix just wants the coefficients on x1 and x2 in order. So I'm actually going to get two rows since I have two equations. And we'll say, well, the top row should have the coefficients in order 3 times x sub 1, so I write the 3, 6 times x sub 2, so I write the 6. And then I go to the second equation, and I want the coefficients on x1 and x2 again. If these were out of order, I'd have to make sure I'm putting it in the correct order, but they're already in the right order. So I would say 5 times x sub 1, so I write the 5. And then 7 times x sub 2, so I write the 7. And this is the coefficient matrix of this system. Now the coefficient matrix is going to be helpful to us, and certainly we talk about it a lot. But for solving systems, we really need the augmented matrix. And the augmented matrix keeps this other set of information that we need. What are these equations equal to? So what we do to build an augmented matrix is we take our coefficient matrix, so I am just rewriting, and then I augment that matrix with the stuff on the other side of the equal sign. So in my favorite, there's lots of different notations you can use. I like to use this vertical line to show that this is the coefficient matrix, and here's going to be my augmented column. So I had 3x1 plus 6x2 and then equals -3, so that -3 should go there in the top row, but in the augmented part of it. And then 5x1 plus 7x2 equals, and then 10. So this is my augmented matrix to the system that we want to be able to work with. Now the size of our matrix tells us how many rows and columns we have. We like to talk about these in general. We also like to get sort of a bit specific too when we talk about matrix operations. We have an n by n matrix as a rectangular array with, so let me sort of write this down again, n by n matrix has m rows and n columns. So the number of rows we have would be for m, and n would be the number of columns we have. So when given the size, we're talking about the rows and then the columns. So if I go back up here, if I want to figure out the size of these matrices, my coefficient matrix, I have 2 rows, row 1, row 2. And how many columns do I have? I want to sort of look from the top here. 1, 2 columns. So I have a 2 by 2 matrix. I have 2 rows and 2 columns. And if I look at this augmented matrix, I see, okay, I have 1, 2 rows. But for my columns, I have 1, 2, 3 columns. That's a 2 by 3 matrix. 2 rows, R for row, 3 columns, C for column. So we designate how many rows we have first and then how many columns we have. Let's go ahead and talk about the methods that we use to try to solve the systems of equations. Our goal is to get the matrix into triangular form to reduce, and we'll be talking a lot more, not only in the next section, but actually throughout the course, about proper row reduction etiquette, what we should do, what we shouldn't do, how we can sort of start by approaching and use sort of a method to solve. But let's go ahead and let's actually just jump into it and start getting some practice right away. We have 3 elementary row operations that we can take advantage of. The first is replacement. We can replace a row by the sum of itself and the multiple of another row. And the wording here is very particular. So I would want to replace a row, but I wouldn't want to be scaling that row that I'm replacing. I can scale another row for the row replacement, and I'll reiterate this fact later on in the course. I think once we see some examples, it'll start to make sense what we're saying here. But very important that we're replacing a row by the sum of itself and the multiple of another row. So if I'm multiplying any row, it has to be the other row, not the row that I'm currently replacing. We can also interchange. We can interchange 2 rows, which is really just switching where they are as rows go. And then scaling says we can take a row, we can multiply all of the entries by a constant, provided that constant is not 0. I don't want to multiply by 0, that'll actually kill off the equation, and that's a very unfair thing to do. But let's actually take a look at this augmented matrix that we have here. So 3, 6 augmented with -3. And then what was that? Second row was 5, 7 augmented with 10. And let's go through some row reduction. Get our first row reduction out of the way, because there's going to be a lot of row reduction in the semester. So let's go ahead and get it out of the way. One of the first things I might notice looking at this first row is that everything is a multiple of 3, so I can scale. And I like to sort of put a little note next to the row that I'm changing. I'm going to do 1/3 times row 1. And it's important that you mention what you're doing, so make sure you're doing this on exams and assessments. I want to know what row operations you're doing, so jot them down. If there's other ways to notate this, this is my preference. So if I multiply everything in this row by 1/3 or divide by 3, I get 1, 2, augmented with -1. So everybody got divided by 3. I'm just going to rewrite row 2. Now, as we move on in the course, we're going to get a little bit better at row reduction. We're going to streamline the process. We're going to move through it quicker. But since this is our very first example, let's take it slow. I can go to this top row, and let's say I want to multiply everything by either a 5 or a -5. Let me just multiply by a 5. There's actually a few different ways you could approach this. So if you would do something different, then hey, I think that you probably know what's going on already. If I multiply this first row by 5, I'm going to get 5 times 1 is 5, 5 times 2 is 10, and then augmented with 5 times -1 is -5. And I can still rewrite row 2. But now what I can do is I can go to row 2 and I can actually do some replacement. I can replace row 2 with row 2 minus row 1. And we'll say, well, how does that look? Well, I'm going to start by rewriting row 1, sort of get that out of the way. But here I'm going to get 5 minus 5, so every entry of row 2, I'm replacing it with row 2 minus row 1. So first I would get 5 minus 5 gives me 0. Then I would get 7 minus 10 gives me -3. And then I would get 10 minus -5. And just be careful with your arithmetic. Nobody likes doing arithmetic. Make sure you have enough coffee. Get your Starbucks. 10 minus -5 is 10 plus 5 gives me 15. So now this looks really good. And what I can do now, and if we'd like to sort of make this a bit of a faster process, is we can kind of double dip. I'm going to scale both of my rows in just one sort of step here. So I'm going to divide every entry of row 1 by 5. So I'm going to replace row 1 with a 1/5 row 1. I'm also going to do something similar in row 2, but here I'm going to divide by 3. And in fact, what I think is better is to divide by a -3. So I'm going to do a -1/3 times row 2 for row 2's position. How is this going to look? Well, if I divide everything by 5 in row 1, I'm going to get 1, 2 augmented with -1. That looks familiar. If I divide everything in row 2 by a -3, 0 stays 0. Here I get positive 1. And then in the augmented cell, I'm going to get a negative 5. So sort of flipping the sign and dividing by 3. Now I'm actually almost done at this point. What I want to do is I actually want to use this 1 here in row 2 to try to get a 0 above it. And we'll talk a lot more about this as a process in general in the upcoming sections, but we'll see that this is actually the best way to go about to use what's sort of referred to as a leading one to eliminate other entries in the column. So let me go to row 1 with that in mind. I'm going to replace row 1 with row 1 minus 2 times row 2. Now, that's where we're headed. That might seem sort of a bit exhausting to think about right now. So it's always okay, whenever you're doing row reduction, to take some baby steps. So another thing I could do, for example, is I could go to this row 2 and I could say, well, since it's our first example, let's do 2 times row 2. Just take it nice and slow. So that's going to give me 0, 2, augmented with negative 10. And I can rewrite row 1. And now I can actually go to row 1 and replace row 1 with row 1 minus row 2. Since I already scaled that up, I can replace row 1 with row 1 minus row 2. And this is a bit of sort of a leisurely row reduction. This is not the fastest way we could do this. We're going to get there. But let's take it nice and easy for this first video. So I get 1 minus 0 is 1. 2 minus 2 gives me that 0 that I wanted. And negative 1 minus negative 10, so that's negative 1 plus 10, gives me 9. And then I can rewrite row 2. Now what I can do, and I am actually almost done at this point, is I can scale row 2. So I can replace row 2 with a 1/2 row 2. So here I have 1, 0 augmented with 9. And then here for row 2, I'm going to get 0, 1 augmented with negative 5. Now at this point, I want to think about what this augmented matrix really represents. It's telling me the solution now to the system of equations. And if I write this out very literally, this top row says 1x1 plus 0x2 equals 9. And the second row says 0 times x1 plus 1 times x2 equals negative 5. But if we think about what this is really saying, is 0 coefficients are going to kill off those terms. So here I really have x1 equals 9, and x2 equals negative 5. And that this is going to be my solution. So if I wanted something that's going to work for these equations, what can I plug in for x1 and x2 into both of these equations that will generate true statements for each of those? Well, I have those numbers now. x1 would be 9 and x2 would be negative 5. And both of those are going to work. You can check it after the fact. The two matrices are called row equivalent if there is a sequence of elementary row operations that transforms one matrix to the other. And what's really nice about these row operations is that they're completely reversible, so I can undo anything that I do in the process. If the augmented matrices of two linear systems are row equivalent, then the two systems have the same solution set. And what we're going to take a look at now is we're going to focus on just getting a bit more practice with these row operations. So here I have already a really nice looking matrix, but I want to try to solve a bit further. And again, we'll get into a bit more about the proper etiquette, but here I can actually start all the way at the bottom, and I'll notice that I have a lot of these zeros here in the coefficient matrix, except I have this 1 at the very end. And I can use that 1 to get zeros entirely above it in its column. Now I already have some zeros there, but this negative 3 directly above it, it's got to go. It's got to go. So what I can do is I can replace in row 3, I can replace row 3 with row 3 plus 3 times row 4. I'm trying to think, how can I get this into a 0? I want negative 3 plus 3, or that's negative 3 plus 3 times 1. So I'm going to replace row 3 with row 3 plus 3 times row 4. Now I'm going to start by just rewriting rows 1 and 2. Just rewrite them. Get that out of the way. But now I'm working in row 3. I get 0 plus 3 times 0 gives me 0. And then again, 1 plus 3 times 0 keeps my 1 there. It preserves it. But negative 3 plus 3 times 1 gives me that 0 that I wanted. And then now I have to work in the augmented entry as well. I want 2 plus 3 times 4. That's 2 plus 12 gives me 14. And then I can just rewrite row 4 if I haven't already. So now row 4 looks good, row 3 looks good. I actually have these pieces to my solution, but now I want to work in row 2. And so as I go in, I see that I can use now this 1 in row 3 to get zeros above and beneath it in its column. And I already have a lot of zeros, but that negative 2 has to go. So I can work with row replacement in row 2. So I could say, let me replace row 2 with row 2 plus 2 times row 3. I can start by rewriting row 1, so that's 1, negative 1, 0, 0, then augmented with negative 5. For row 2, I'm going to get 0 plus 2 times 0 gives me 0. 1 plus 2 times 0 keeps my 1. Negative 2 plus 2 times 1 gives me negative 2 plus 2 gives me 0. That's the 0 I wanted. And then 0 plus 2 times 0 keeps my 0. And then in the augmented entry, I'm going to get negative 7 plus 2 times 14, where that's negative 7 plus 28. That's going to give me 21. Just be careful with the arithmetic. And then I can rewrite rows 3 and 4, just as they were. So just rewriting. Now I can go ahead and try to finish this process. So now I'm going to use this 1 in row 2. It's the only one in the coefficient matrix for that row. I'm going to try to get rid of all the entries above and beneath it. I want them to all be zeros. I see I have the zeros underneath, but what about above? I got to get rid of that minus 1. So I'm going to do that. I'm going to replace row 1 with row 1 plus row 2. So I get 1 plus 0 gives me 1. Negative 1 plus 1 gives me 0 that I wanted. 0 plus 0 gives me 0, and then again. And then in the augmented entry, negative 5 plus 21 gives me 16. I can go ahead and rewrite the rest of these. And now if I look at what I have, these are very sort of boring rows to work with. They're giving me all of the pieces of the solution. This first row says x1, and then all these zeros mean the other variables are getting killed off by their coefficients. x1 equals 16. Second row tells me x2 equals 21. The third row is telling me it's really saying 0x1, so you're gone, plus 0x2, so you're gone, plus 1x3, plus 0x4 equals 14, so x3 equals 14. And then that last row is telling me x4 equals 4. And this is my solution to the system. We got our solution. Let's take a look at another example. It's all about building practice. I see I already have a couple parts to my solution already. Rows 3 and 4 look great, but let me work now in row 2. And I want to get rid of this 3 here, and I can use row 4 to do that. Say, well, let me go into row 2, replace row 2 with row 2 minus 3 times row 4. I go ahead and start by rewriting row 1. Just get that out of the way. Then in row 2, I get 0 minus 3 times 0 gives me 0. 1 minus 3 times 0 keeps my 1. I'm going to get 0 minus, oh sorry, using row 4. So 1 minus 3 times 0, 0 minus 3 times 0 is going to give me 0. And then 3 minus 3 times 1 is going to give me that 0 that I wanted at the end there. And then here in the augmented entry, 6 minus 3 times negative 2. Be careful with those minus signs, right? So 6 minus negative 6, that's 6 plus 6, gives me 12. And I can rewrite row 3. There we go, and I can rewrite row 4. So it looks good. Now I'm ready to take a look at what's happening in row 1. And there's a lot of stuff I want to get rid of. I just want this 1 at the very front. I'm going to try to get rid of the 3 and the negative 2. Let me do that in stages. Let me first get rid of this negative 2. So I'm going to replace row 1 with row 1 plus 2 times row 4. So Here I get 1 plus 2 times 0 gives me 1. 3 plus 2 times 0 gives me 3. 0 plus 2 times 0 gives me 0. Negative 2 plus 2 times 1 gives me negative 2 plus 2 gives me 0. And then augmented with negative 7 plus 2 times negative 2, that's negative 7 plus negative 4 gives me negative 11. And I can rewrite the rest of the rows. And now I can work in row 1 again. I still want to finish this up. I want to get rid of this 3, so I can use row 2 to do that. So say, well, let's go ahead and replace row 2. Well, we'll replace row 1. We're working in row 1, so I'm going to replace row 1 with row 1 minus 3 times row 2. So I get 1 minus 3 times 0 gives me 1. 3 minus 3 times 1 gives me that 0 that I wanted. 0 minus 3 times 0 gives me 0, and then again. And then augmented with, now I want negative 11 minus 3 times 12. Now keep in mind, so we're doing a lot of arithmetic here. No shame in going to the sort of side or the margin and saying, okay, so what's going to happen there? I want negative 11 and then minus 3 times 12. Let's see what that's going to look like. So that's negative 11 minus 36. That's going to give me negative 47. And then I can rewrite the rest of the rows. So 0, 1, 0, 0, augmented with 12. 0, 0, 1, 0, augmented with 2. And 0, 0, 0, 1, augmented with minus 2. Now I have the solution. I'm sort of staring at it. I just have to be able to interpret it. This first row is saying x sub 1 equals negative 47. Second row is saying x sub 2 equals 12. Third row is saying x sub 3 equals 2. And the fourth row is saying x sub 4 equals negative 2. And this would be my solution to the system. Let's see one more example, and then we'll talk a little bit more, and then I think this will be a good introduction. Right now we're just building the mechanics, getting comfortable going through the problems. Let's solve the given system of equations. So this looks a bit more like what we think of when we think of a linear system, but the goal is to write this into an augmented matrix. And I want to be very careful when I'm doing this. So I have to make sure I have all my coffee, that I'm not falling asleep on the job. When I write out my coefficient matrix, I notice x2 is missing. So that must really be a 0x2 term that got sort of, killed off. So I have 2x1, so 2 should go there. We said x2 is missing, so that's a 0x2. And then I have negative 6x3, so negative 6, and then augmented with minus 8. For row 2, I don't have x1, so that should be 0x1. I have 1x2, 2x3, so write the 2, and then augmented with 3. And then here, this last one, not really trying to trick me, I can see all the pieces. I have 3x1, 6x2, negative 2x3, and then augmented with minus 4. So this is my augmented matrix that I get. Now I'm ready to start working with my row operations. This top row, I could actually scale it. I can divide everything by 2. I think that's a good move to make. So I'm going to replace row 1 with 1/2 row 1. And that's going to give me 1, 0, negative 3, augmented with minus 4. Row 2, I'm just going to rewrite. And then row 3, I'm going to rewrite as well. Now what I can do is I can actually use this 1 here in the upper left corner to try to get zeros underneath it. And what I can do is I can actually then work in row 3. I see the 0's already in row 2, but I got this 3 in row 3 I want to get rid of. So let me go ahead and replace row 3 with row 3 minus 3 times row 1. I want to get a 3 minus 3, so I can do that by replacing row 3 with row 3 minus 3 times row 1. And just to get out of the way, I'm just going to rewrite rows 1 and 2. But then in row 3's position, I get 3 minus 3 times 1 gives me 0, like I wanted. 6 minus 3 times 0 gives me 6. Negative 2 minus 3 times negative 3, so that's negative 2 plus 9, gives me 7. And negative 4 minus 3 times negative 4, that's negative 4 plus 12, and that's going to give me 8. So looking not so bad so far. Now so if I'm doing this sort of looking at the columns, that first column looks really good. But if I'm moving to the second column, I want to use this 1 in row 2 right in the middle of my coefficient matrix. I want the 0 above it. I got it. I want the 0 underneath it, which I don't have. So I want to get rid of that 6. So what I can do then is I can do a row replacement in row 3. And I can replace row 3 with row 3 minus 6 times row 2. So let me rewrite rows 1 and 2. Just get that out of the way. And here I get 0 minus 6 times 0 gives me 0. 6 minus 6 times 1 gives me that 0 that I wanted. 7 minus 6 times 2, or that's going to give me 7 minus 12 is going to give me negative 5. And then augmented with 8 minus 6 times 3, that's 8 minus 18, gives me negative 10. And then looks pretty good so far. But now with row 3, I can actually just scale this to make it look a little bit nicer. So I'm going to replace row 3 with a negative 1/5 row 3. I'm going to divide each entry by a negative 5. So that gives me 0, 0, positive 1, augmented with positive 2. And I can rewrite the other rows. Now, first column looks great, second column looks great, third column has a lot of work left in the coefficient matrix. I want to use this 1 in row 3 to get rid of the entries above it. I want that 2 to be a 0, I want that negative 3 to be a 0. And you can do this in 2 separate steps, or if you really like row replacement, you could actually do it right at once. So I'm going to replace row 1 with row 1 plus 3 times row 3. But I'm also going to want to either now, which I'm going to do, or in another step would be fine too, is replace row 2 with row 2 minus 2 times row 3. Yeah, I'm going to rewrite row 3 just to get that out of the way. I'm going to use that to do some elimination in rows 1 and 2. So focusing on row 1, replacing it with row 1 plus 3 times row 3, I get 1 plus 3 times 0 is 1. 0 plus 3 times 0 keeps my 0. Negative 3 plus 3 times 1 gives me that new 0 that I wanted. And negative 4 plus 3 times 2, that's negative 4 plus 6, gives me positive 2. And then I can work in row 2 as well. So I get 0 minus 2 times 0 gives me 0. 1 minus 2 times 0 gives me 1. But then here 2 minus 2 times 1 gives me that new 0 that I wanted. And 3 minus 2 times 2, that's 3 minus 4, gives me negative 1. And now this is completely reduced, and I can actually just pick out my solution. So that first row is saying x1 equals 2. Second row is saying x2 equals negative 1. That last row is saying x3 equals 2. And there I have my solution. Let's do a couple more examples, but let's sort of focus a bit on things a bit more interpretive. I want to determine the values of h that make the augmented matrix a consistent linear system. And here I have 1h augmented with minus 5. So I say, well, what's going on with h? Well, we're going to find that out. And then 2 negative 8 augmented with 6. Now, right away to start, I would notice that row 2 could actually be scaled. I could do a 1/2 row 2. So I'm going to rewrite row 1. That's 1h augmented with minus 5. Row 2, I'm going to divide everything by 2. That's going to give me 1, negative 4, augmented with 3. And then I can start doing some row reduction. And let me actually work in row 2. I'm going to replace row 2 with row 2 minus row 1. So row 2 minus row 1. So I'm going to rewrite row 1. But in row 2's position, I get 1 minus 1 gives me 0. Negative 4 minus h, I don't really know what that looks like because I don't know what h is, but that's the value that should be here, so I'm just going to write it. Negative 4 minus h. And then 3 minus negative 5, or that's 3 plus 5, gives me 8. Now I want to focus on what this second row is telling me, and I actually can now make some comment about it So that second row is saying 0x1 plus, here my coefficient is kind of funny, it's negative 4 minus h all times x2, and then equals 8. And 0 times x1 is really just 0. It's going to kill off that variable for this second row. So I can really just focus on negative 4 minus h as my coefficient times x2 equals 8. However, there's a bit of a problem that could happen here. Something to consider as a potential issue would be, well, what if I had something that said 0x2 equals 8? This doesn't make sense, right? This would be saying 0 equals 8, and we know this to not be true. So it makes us very sad and frustrated. So I can actually make that comment right here and say that since my coefficient on x2, really it shouldn't be a 0. Anything else is fine, because if this was any other number, I could just solve for what x2 is. And so we're really making the claim that negative 4 minus h should not be 0. If it is, then this is what I get, and that doesn't make any sense. It would give me an error. And so then solving this, what this is really saying is that h should not be negative 4. Right, so h should not be negative 4. And another way that I could sort of see this or try to visualize it is if I just divided to try to solve for x2. If I went through and did the scaling, I'd say, well, let me scale this. x2 would be equal to 8 divided by negative 4 minus h. And this is fine except for when h is negative 4, where I get a division by 0. So in fact, h can be anything so long as it's not negative 4. So we can make a bit of a comment here. H can be anything it wants to be except negative 4. If h is negative 4, we have an inconsistent system with no solution. We get a false statement. Let's see a similar example. Determine the values of h that make the augmented matrix a consistent linear system. Now in this case, I want to do something similar in my approach. I can actually scale up row 2. I could scale down row 1. I think that would look nice as well, but I'd be dividing, something that I don't know what it is by something else, which is okay in this case, but I think aesthetically it would look nicer if I'm just willing to scale row 2. And here I could scale row 2 by a negative 2. So let me rewrite row 1. Just rewriting row 1. And then scaling row 2, negative 2 times 2 gives me negative 4, negative 2 times negative 6 gives me positive 12, negative 2 times negative 3 gives me positive 6. Now I can start working through some row reduction, and in fact, I can work in row 2, replacing row 2 with row 2 minus row 1. So let me rewrite row 1. Just get that out of the way, just rewriting it. But then in row 2's position, negative 4 minus negative 4 gives me 0. 12 minus 12 gives me 0. And then augmented with, I would have 6 minus h. I don't know what that is because I don't know what h is, so I can just kind of write that out as 6 minus h. But if I focus on what this second equation is telling me, the second row as an equation, I should say, it's saying 0x1 plus 0x2 equals 6 minus h. Well, 0x1 and 0x2 are both just 0, so this is really saying 0 equals 6 minus h. Now, in order for this to be a true statement, there's really only one possibility for h in this case. Right? H would have to be 6. I can literally solve this for h and say h is equal to 6. So the only way I'm going to get a consistent system out of this is if h is the value 6. No other values would work. I think in this last example, anything would work except negative 4 wouldn't. In this example, only 6 would work for h. A couple of questions I want to leave you with before we end this introduction lecture is about the existence and uniqueness when it comes to finding solutions. So two big questions that we have about a linear system are the following. First, we want to know, is the system consistent? I want to know, is there a solution to this system? I'm going to try to solve it. I want to know, is there a solution? If there is a solution, we have sort of a secondary question that we want to ask ourselves. If a solution does exist, we want to know, is that the only solution, and is the solution unique? And I'm sort of covering it up here with my face. We want to know, is the solution unique? Meaning, since there's a solution, is it the only solution, or are there infinitely many solutions? All right, that's of course the question, right? So I want to know, is there a solution? Is the system consistent? And if it is, I want to know, is there just the one solution, or are there other solutions out there, infinitely many? Hey, I want to say thank you so much for hanging out with me, talking a little bit about an introduction to our course material. We're going to be back at it soon with more of these lecture videos, more row reduction. Make sure you're getting the practice in. I want to say, no matter where you are and what you're doing, to always keep learning, keep dreaming, and always follow your heart. And I'll see you next time. Until then, take care.